Hello and welcome to Arithmetica and the first video introducing proof and reasoning. We begin with providing the notion of logic and language used in mathematics before exploring some of the basics of logical proof. This will help pave the way to Arithmetica's introduction to propositional logic, which is an important prerequisite to the development of formal systems in mathematical logic. However, as a basic introduction to logic, we shall start with deduction, followed by another form of logical inference called induction, before swiftly moving on to our introduction of abductive inference, which we will be covering in greater detail in future videos as part of Arithmetica's program in proof and reasoning. Mathematical logic can from time to time leave one a little unsettled, as if one was uncertain whether one should knock on the door to the mathematics or perhaps the philosophy department, if it was not for its level of formality and the simple truth that mathematicians are able to enjoy the firm foundations upon which their proofs can be constructed, owing to the rigours of mathematical logic. Indeed, in modern mathematics, the ability to write proofs is essential. But what exactly constitutes a mathematical proof? In mathematics, we are, in general, interested in establishing the truth of a statement, a sentence that is either true or false, the philosophy being that the notion of truth is absolute, and as such there cannot be any ambiguity. Thus a statement cannot be true and false, and can therefore be only one or the other, a concept in the study of formal systems called consistency. Therefore, we would not be interested in statements like Jill is pretty, or Bob is handsome, as it's a matter of opinion and as such highly subjective. This absolution of truth carries with it a greater sense of security than say in the relativistic perception of truth. For example, suppose some bath water is run and two people are invited to dip their hands into the water, so to assess its temperature. It is by no means certain that there would be agreement between the two volunteers. With two different opinions, one might be tempted to claim that truth is relative. However, someone of whom is familiar with thermodynamics might make the point that people make poor thermometers, and that the body responds to the heat energy transfer. That is, if someone was of the temperature of the bath water, so that there is negligible heat energy transfer between them and the water, then it would be said that they are in thermal equilibrium. Anyone else who is not in thermal equilibrium with the bath water would either find the water colder or hotter, respective to the net heat energy being transferred away or into their body. The fact of the matter is, the water, assuming it has been mixed uniformly, will be at a given temperature at the instant the assessment is made by our volunteers. Place a thermometer into the bathwater, and regardless of the subjective opinion of any person's own perception, it will give a measure within some level of accuracy of the temperature. Thus, without getting too involved in the complexities of thermodynamics, and certainly such that for this argument quantum effects are negligible, owing to the apparent continuum of the energy when considered beyond that of the microscopic, there is only one truth, and as such is absolute. Moreover, a mathematical proof contrasts to what we might conceptually recognize as proof in our everyday language, or even to that of scientific proofs. In science, a hypothesis is developed from observation and analysis of a physical phenomenon in order to describe it. Any such further observation of the phenomenon that compares well to the hypothesis contributes to evidence in its support. Additionally, under very strict control conditions in a manner that can be repeated in other suitably equipped laboratories, the appropriate scientific experiments are carried out so to test the hypothesis. This includes the assessment of its predicative abilities and to reveal any possible flaws. If under such conditions the hypothesis continues to be successful, it is declared scientifically proven and is accepted as a scientific theory. In contrast, a mathematical proof of a proposed conjecture constitutes the conclusion of a process of deductive reasoning based upon a collection of accepted, often self-evidently true statements called axioms. If the logical deduction is flawless, then the conclusion must also be true, thereby elevating the conjecture to a mathematical theorem. This follows from the accepted truth of the axioms in force and what is called logical validity. That is, the truth of the assumptions or axioms in force of a process of deductive reasoning guarantees a true conclusion. As a side note on terminology, the proven statement is often referred to as a theorem if it is a key result, a lemma if it is a minor result, or for example a corollary if the result immediately follows from another established result. In any case, it is this level of rigour which renders a notion of absolution in a mathematical proof. Thus, when a mathematician provides a valid proof, they can be certain it will never be disproven. That is, once proven, it remains true for all time. The same cannot necessarily be said to be true for a scientifically proven theory, which in the developing nature of science might one day lead to an experimental means of disproving such a result. To provide something of a demonstration of two different methods of proof, mathematical and scientific, let us consider the following two examples: a 3-card problem and the mutilated chessboard problem. Suppose 3 cards are placed face down on a table, such that 2 are jokers and the other is a king. You are informed that if you correctly guess the location of the king, wins you the game. You make your choice, and subsequently one of the other 2 cards are turned over to reveal one of the 2 jokers. You are then given the option to switch to a different card, or remain with your original choice. Now, most people are perfectly content in sticking with their original choice, and why not? After all, by revealing one of the 2 jokers, you now know that the remaining 2 cards must be a king and a joker. Clearly, this is equivalent to having been presented with 2 cards, one a king and the other a joker, and being asked to guess where the king is. That is an equal chance in correctly choosing the position of the king, whether you stick with your first choice or change your mind. A 50-50 chance, one way or the other. I mean, it's just common sense, right? Well, wrong. The problem is, what we generally refer to as common sense is not a valid branch of logic. Common sense is fine for everyday problem solving, but for problems of a more advanced nature, inclusive of probability, it's just unreliable. So what would be a more reliable approach? Let us start with the mathematical method, i.e. deductive reasoning. And so, to help us in presenting the deductive approach, I am pleased to announce Arithmetica's resident mathematician, aka the Math Magician. Either your first choice is a king or otherwise it's a joker. Suppose it's a king, then the other two cards are jokers. Clearly, by not switching guarantees a win, while changing your mind results in you losing. Suppose now that your original choice is not a king, then there are two possibilities where the king is, namely one of the other two cards. Clearly, in both cases, sticking with your original choice will result in losing the game. So consider then you changing your choice. By switching, we now know you will not choose one of the jokers, and obviously you don't choose the other card, which has already been revealed to be a joker by the dealer. Therefore, by changing your choice, you are certain to select the king, and in doing so win the game. But there are two possibilities when your original choice is not a king and therefore a joker, corresponding to the two remaining cards. Now, the probability of an event is the measure of the likelihood that the event occurs. Mathematically, it is defined to be the ratio of the number of times an event can occur from what is called a probability space to the total number of possible outcomes. Thus, if P of E is the probability of event E occurring and S represents the probability space, then we have P of E is equal to the number of possible outcomes in E divided by the total number of possible outcomes in S. This is often referred to as the theoretical probability of an event and is generally regarded as the ideal or purest evaluation of the chance of an event occurring. It is also known as classical probability, in which it is generally assumed that in a physical system where there is limited knowledge that we may treat each possible event as being equally likely to occur. This fundamental property of classical probability is called the principle of indifference. So, returning to the problem. From the aforementioned argument, there is only one possible outcome for a win, when our original choice is a king, and two possible outcomes for a win otherwise. Thus, in total, there are three possible outcomes to win the game. That is, if we change our mind and choose a different card, then there are two possible outcomes of a win, while if we do not change our mind, then there is only one outcome which guarantees a win. Thus, there is a 2 out of 3 chance of winning if we change from our original choice, as compared to only a 1 in 3 chance if we keep with our original selection. Therefore, from our logical analysis, and as shown in the following table, the probability of winning as a consequence of switching your original choice is 2 over 3, which is twice as likely in winning the game than the probability of not switching, with probability 1 over 3. We conclude that the best chance of winning the game is by accepting the option to switch from your original choice. We now turn our attention to what we could describe as the scientific method, which is concerned with the collection of data and evidence. And what better way to help us do this than with the aid of Arithmetica's scientist, known simply as the Professor.
It was you!
Oh, sorry, my mistake. We begin by playing the game a few dozen times and record whether we win if sticking with our original choice or if by switching to the other card. This might be sufficient to gain some insight, but to render it statistically viable, we would need to continue until a clear pattern emerges. Now, when collecting data, we use a slightly modified form of the definition of the probability of an event occurring. It is based on direct observations or experiences of events, and mathematically is the number of times an event is observed to occur divided by the total number of observed occurrences. Thus we may write, this definition is called empirical probability or statistical probability, and it is understood that its reliability improves as more data is collected. That is, it tends to the theoretical probability. In the case of the 3-card problem, the above approach would require the observed occurrences to become arbitrarily large, i.e. tend to infinity. Therefore, the empirical probability of an event is, in general, only an estimate of its ideal or theoretical probability. If then the game is played a sufficiently large number of times, so to reveal a reliable pattern of outcomes, then we would expect the empirical probability of winning to agree, albeit approximately, to our mathematical derivation shown earlier. Try it yourself and see. In any case, these two results show how careful we need to be considering that the original common sense argument was flawed. Many people seem to have an overabundance of confidence when arguing their opinions, particularly those problems of or relating to probability. But I hope that the previous demonstration shows that probability can be a bit of a slippery character and deserves a little more respect. In fact, this game in probability is often presented in the form of a game show, popularised by the American television programme Let's Make a Deal, originally aired in the 1960s and 70s and hosted by the Canadian-American presenter Monty Hall. Consequently, this variant of the problem is usually named the Monty Hall problem, after the host of the show. The contestant, rather than being dealt with 3 cards facing down, is faced with 3 closed doors. The contestant is then told that there is a goat behind one of the 3 doors, and that they are tasked with the job of guessing which one. As with the card game, after the contestant makes their choice, they are given the option to change their mind, but here it is once the host opens one of the other 2 doors to show that there is no goat. And so this brings us to the mutilated chessboard problem as our next and final example of 2 methods of proof. We start with a chessboard and then remove the 2 opposing corners, say the 2 opposing white corners, leaving 62 squares in total. Assume that there is a set of dominoes such that any one domino covers exactly 2 of the squares on the chessboard. The objective is to determine if it is possible to cover all 62 squares on the chessboard with exactly 31 dominoes. This time we apply the scientific method first, that is by experimentation. The scientist would try a few different ways of arranging the 31 dominoes on the chessboard, noting that every such attempt fails to provide a solution. To induce further rigour, the scientist will endeavour to continue with various arrangements before they believe that there is sufficient evidence to conclude that such an attempt to cover the chessboard with 31 dominoes is impossible. However, the conclusion is a theory based on experiment, and so the scientist will never know out of millions of possible ways of covering the board there exists an arrangement demonstrating a solution to the problem, which they have not tried. Of course, if the problem can be solved and an arrangement was found, then we have empirical proof that the chessboard can be covered in the way as stated in the problem, and no further investigation is required. After all, we need only one such arrangement. Firstly, we note since there are 62 squares remaining on the chessboard and that each domino covers exactly 2 squares, then we would require a minimum of 31 dominoes, so the problem has at least some chance of success. Now, a chessboard consists of 32 white squares and 32 black squares. Thus, on removing 2 white squares from the board, there are now only 30 white squares and 32 black squares. However, due to the way in which the squares on a chessboard alternate in colour, each domino must cover exactly 1 white and 1 black. Therefore, for any arrangement of 31 dominoes, 30 cover exactly 30 white and 30 black, leaving 2 black squares to be covered by a single domino. But this is impossible because each domino covers 2 neighbouring squares and are opposite in colour on a chessboard. We conclude that no arrangement exists in a manner that would allow 31 dominoes to cover all 62 squares on the mutilated chessboard. Thus, the mathematician arrives at the same conclusion as the scientist, but with the added advantage that their conclusion is certain to be true. Of course, in reality, a scientist will be more than capable of logical thought, given the nature of their profession, and will have the necessary deductive skills as part of their education in applying the so-called mathematical method in solving both of these problems. Indeed, the mutilated chessboard problem and a 3-card problem, or otherwise the Monty Hall problem, simply demonstrate the difference between mathematical proof and scientific proof, and helps show how powerful deductive reasoning can be. Join me again in the next video in this series when I shall be explaining some of the basics in logic, and in particular deduction. And so, until next time, it's goodbye from Arithmetica. How am I expected to do recording with you on my shoulder? You're like a warm, furry scar.